Hello everyone, my name is Sathira Wickramanayake from the University of Technology Sydney, Australia. I am presenting the paper titled Deep Learning Ground Penetrating Radar Subsurface Features for Robot Localization. So first I will talk about some background and the motivation for this research. So sensors are used in robotic applications to provide a way for the robots to perceive the environment and also localize itself. And traditional sensors such as encoders, GPS, cameras, or LIDARs may not be capable for navigating in changing environments, or places with no GPS signals, or terrains where encoders will not be accurate. Some example scenarios would include underground in-pipe robots and also floating robots. So in this paper, we present a method that uses GPR features to determine the 1D odometry of a robot in an environment that has frequent changes in visual features and also that can lack GPS reception. And this method also does not require the distance that is typically obtained from a wheel encoder, making this a very good option even for wheeled robots that navigate very uneven terrains. So here's some introduction to ground penetrating radars, or GPRs. GPR transmits radar pulses through the ground surface and receives reflections from the subsurface dielectric material changes. And the difference in the relative permittivities of the two materials would control the reflection amplitude. And GPR data is generally interpreted as B-scans, also called as brightness scans. These B-scan images show subsurface features of an object in the form of signal reflections, similar to what we can see here in this example B-scan image. And since the GPR is capable of capturing features below the surface, which are less likely to change over time, GPR signals are a great form of robot perception for navigating in constantly changing external environments. So in this work, we use the deep learning framework to estimate the odometry using the B-scan images. And before feeding the data into the deep neural network, we have to do some pre-processing. So during pre-processing, we do the following steps. We first apply a dewav filter to remove any very low frequency noise, and then we apply a bandpass filter to remove any high frequency noise. We also add a background subtraction filter to remove the repetitive constant reflections that could happen in the B-scans. And these filtered B-scan images are then combined to build pairs of consecutive B-scans, which we call a subsequence. Then these pairs are concatenated to form an image with 6 channels that can be fed into the neural network. So here you can see the difference between the filtered and the unfiltered B-scan images. So the first 2 images are the unfiltered and the filtered B-scans of the 100 subsequence, and then the other 2 images are the same of the 110th subsequence. So we can see that the filtered images clearly shows the subsurface features more prominently than the unfiltered images. And with the green dotted box here, I have highlighted some subsurface features, and we can see the displacement of these features very clearly on the filtered images between the subsequent B-scans and not so clearly on the unfiltered images. Yeah, so this is a very high-level diagram of the deep learning framework that we use to estimate the odometry using GPR B-scan images. So now I will go through briefly the steps in this diagram. So as we can see here, after the image filtering and the subsequencing step, we are using convolutional neural networks to extract the features from the B-scan images. And the feature extraction part consists of 2D convolution layers, batch normalization layers, max pooling and dropout layers. After that comes the regression component. And since the distance traveled by the robot always depends on its previous position, this becomes a sequence learning problem. Therefore, we had to use a recurrent neural network, or an RNN, to determine the distance traveled across the sequence of B-scan images that we feed into the model. And traditional RNN networks have a problem called the vanishing or the ballooning gradient problem. So this occurs when long-term dependencies are learned and grow exponentially more than the short-term counterparts. So due to this reason, we had to use long short-term memory or LSTM networks, which can learn long-term dependencies and solve this vanishing gradient issue. So in this diagram, we can see the LSTM layers at the regression stage of the deep learning architecture, right before the output layer. Okay, so now I will talk about some experimentation and results. So the proposed deep learning framework was evaluated using a publicly available dataset published by CMU, which was collected using a manually pulled experimental rig like the one we can see here in this diagram. So this rig contained multiple pieces of hardware, including a Noggin 500 GPR, a very high resolution encoder, an Xsense 9-axis IMU, and also an Intel RealSense camera. A robotic total station was also used to obtain the 2D ground truth location of the rig as it was moved along different trajectories. As this dataset was acquired indoors on a flat surface, the platform wheels did not slip, making the encoder data nearly identical to the ground truth. But in most real-world applications, wheel encoders collect errors as the robot loses wheel contact, causing erroneous reading. So to emulate a realistic wheel encoder, what we did is we included a stochastic odometry drift onto the dataset. So in this figure here, on this graph here, we can see that the ground truth plotted in blue, which is very similar to the encoder readings plotted in green. And the black line here shows the altered wheel encoder odometry, produced by including the stochastic drift, which represents a more real-world robotic application. So here are some results that we obtained using the CMU dataset and our developed deep learning framework. So with a total of 11 sequences of data collected, we used 7 of them as training data, and sequences 1, 3, 7, and 9 was used as testing data. The model was trained using the Adam optimizer and a learning rate of 0.0001. The average batch mean squared error of each test sequence was calculated to be very low, ranging from 0.115 to 0.403. This proves that the model is performing really well. The predicted results using the deep learning method was plotted against the ground truth and the wheel encoder odometry, as we can see here in these graphs. So the blue line that you see in the graphs shows the ground truth, and the green line represents the accurate wheel encoder data, while the black line represents the altered wheel encoder, which mimics a more realistic robotic wheel encoder. And the red plot shows the odometry produced using the proposed method. And in all the 4 test trajectories, we can see that the odometry was predicted reasonably well and was very close to the actual odometry obtained using the accurate wheel encoders. The odometry estimated using the proposed method was closer to the ground truth than the altered wheel encoder data, which had wheel slip artificially introduced to mimic a realistic wheel encoding system of a robot. This shows that the proposed method does not rely on the accuracy of the wheel encoders. So that was a brief explanation of the work carried out in this paper. And in summary, this paper proposes a deep learning framework for robot localization based on GPR subsurface features. And some of the key contributions include the development of a deep learning framework that estimates the 1D odometry of the robot to be used in localization applications, which uses convolutional neural networks for the feature extraction from GPR B-scan images, and long short-term memory networks for 1D odometry estimation. And the evaluation was done using a publicly available dataset, and the results demonstrated that the proposed approach could localize a robot without the need for the distance information from the wheel encoders, making the results unaffected by wheel slip even in uneven terrain. And in the future, we will include 3D localization using GPR to determine the robot's 3D position, and we will also be using loop closure techniques to improve the localization accuracy. Okay, so that comes to the end of the presentation. Thanks everyone for listening, and if there are any questions, please feel free to email any of the authors.